Assalamualaikum and hi. Today, my group members and I will be presenting a video entitled Electrical Potential Due to Point Charge. My name is Shafika binti Kamaruddin, matrix number B011810099. Today, I will be presenting on theory of electrical potential due to point charge.
My name is Sohail binti Sharif, matrix number B011810034.
Hi, Assalamualaikum. My name is Nur Afika binti Maraif. My matric number is B011810060.
In this video, we will like to explain the theory of electric potential for point charge, followed by two work examples. Let's start with the definition of electric potential due to a point charge. The electric potential at a point is equal to the electric potential energy measured in joules of any charged particle at the location divided by the charge measured in coulombs of the particle. This means that the electric potential indicates how much potential energy a single point charge at a given location will have. Since the charge of the test particle has been divided out, the electric potential is a property related only to the electric field itself and not the test particle. Another way of saying this is that because potential energy is dependent on charge Q, the Q in the equation will cancel out, so V is not dependent on Q. Next, we will move on to electric potential between point A and B. The following figure shows the displacement of point charge Q in an electrostatic field E. Note that, first, in determining VAB, A is the initial point while B is the final point. Second, if VAB is negative, there is a loss in potential energy in moving Q from A to B. This implies that the work is being done by the field. However, if VAB is positive, there is a gain in potential energy in the movement. An external agent performs the work. Thirdly, VAB is independent of the path taken. Fourthly, VAB is measured in joules per coulomb, commonly referred to as volts. Thus, equation 1 is derived, that is, VAB is equal to work done over Q charge equals to negative integration of point A to point B in the direction of dl. As an example, if the electrostatic field E, as in the previous figure, is due to a point charge Q located at the origin, then E will be as shown in equation 2. Then, by substituting equation 2 into equation 1, shown in the previous slide, the electric potential of AB or VAB will be as shown in equation 3. The superposition principle, which we applied to electric fields, also applies to potentials. For n point charges Q1, Q2 till Qn, located at points with position vectors R1, R2 up to Rn, the potential at R is given by the equation 4. Generally, the electric potential for point charges can be denoted as shown in equation 5. Next, we will proceed with electrical potential of a single point charge. The electric potential due to a point charge is thus a case we need to consider. Consider VB and VA are absolute potentials at point B and A respectively. Therefore, the potential difference VAB may be regarded as the potential at B with reference to A. In problems involving point charges, it is customary to choose infinity as reference. That is, we assume the potential at infinity is 0. Therefore, if VA equals to 0 as RA approaches infinity, as in equation, the potential at any point RB approaches to R due to a point charge Q located at the origin is as shown in equation 6. Up next, my friend Swaila will continue with the presentation by showing the work example.
In this part, I will show you one example of electrical potential due to a point charge. Based on the figure, we need to calculate the electric potential of 1 microcoulomb point charge 10 meter away at point A and 200 meter away at point B. Another question is, what is the voltage between point A and point B? The electrical potential can be solved by using formula Q over 4 pi epsilon R, which is R is a distance between charge and a point of interest. For electrical potential at point A, Q is the value of charge, which is 1 microcoulomb divided by 4 pi epsilon times by 10, and we will get the answer 900 volt. For the electrical potential at point B, the value of Q is 1 microcoulomb divided by 4 pi epsilon 200, and we will get 45 volt. As we can see, if the value as it moves away from charge, the electric potential decrease. Next, we need to calculate the voltage between point A and point B. The voltage is the difference between 2 points. So, the voltage is the change in electric potential is different between electric potential at B and electric potential at A. At B, electric potential was 45 and A 900. So, it will give us the negative 855 volt. So, what is meant by that? As we move from point A to point B, the electric potential decreases, and it makes sense because we move away from the positive charge. A positive charge will create a positive electric potential, and negative charge will create a negative electric potential.
In this video, I will explain the example of potential difference between 2-point charges. 2-point charges -4 microcoulomb and 5 microcoulomb are located at 2, -1, 3 and 0, 4, -2 respectively. Find the potential at 101 assuming 0 potential at infinity. Charge 1 is equal to -4 microcoulomb and charge 2 is equal to 5 microcoulomb. The point distance R is equal to 101. The point distance for R1 is equal to 2, -1, 3 and the point distance for R2 is equal to 0, 4, -2. The value of epsilon naught is 8.854 times 10 to the power of -12. The formula of potential R is equal to charge 1 divided by 4 pi epsilon naught magnitude R minus R1 plus charge 2 divided by 4 pi epsilon naught magnitude R minus R2 plus constant naught. If potential equal to 0 at infinity and constant naught equal to 0, we need to find the magnitude for R minus R1 first. 101 minus 2, -13 and the answer is square root 6. For magnitude R minus R2, 101 minus 04, -2 and the answer is square root 26. Formula potential R is equal to charge 1 divided by 4 pi epsilon naught R minus R1 plus charge 2 divided by 4 pi epsilon naught R minus R2. We need to replace the value of R with 101 and the answer is 5.864 kilovolt.